Welcome back to this lecture on LP norms, where we will talk about a little bit of the various types of LP norms that we have and we are going to be using in this course. So if you have done the previous week's videos, you have already seen this identity called the L1 identity. And L1 identity, just to remind you what this is, so let me put the LP norms title here. And remember that the L1 identity says the following, that if you take mu and nu probability distributions in ZP, then the total variation distance, so if you remember, this was the maximum of the distances of the measures A in ZP, this is equal to a half of the sum, when you sum over the whole group, mu t minus nu t. So this was like the basic identity that we've been using, and it's very important in the later on, especially in the course, that we will need. But then we will later on also start using other types of norms, which help to understand a bit better about the behavior of these random walks. So with the L1 identity, you already see that there is this quantity here. I think I already kind of mentioned this, that the reason why it's called an L1 identity is because of this, exactly this, why we have the this expression. So remember that the L1 norm, we can define that if f is a function, let's say to a complex plane, then we then define the L1 norm, I think I use this notation, to just be the sum of ft, take its modulus, and then sum over the group. So that's the way you can define the L1 norm. So now we can say that d mu nu is equal to a half of the L1 norm of the differences of these two functions, which are the probability distributions, becomes into this form. Okay, now the other types of norms that are like really used are, of course, the so-called LP norms. So let p be a number. It can actually be any number between 1, so it includes a 1 and less than infinity. Then the LP norm of f from ZP to C is defined by just taking this f, p, and we actually put here the sum over t in ZP, ft to the power p, but then we take actually pth root. So they raise it to the power 1 over p. That's why you're assuming that p is less than infinity, so that we can basically define this in this way. So that's the LP norm, okay? So we now have the kind of basic situation. And then the last kind of norm that we encounter, we have kind of already encountered, especially in the so-called variational principle for the total variation distance. We have the L infinity norm, basically meaning that here, so if f is a function from ZP to C, we define the L infinity norm to be equal to this maximum, in our case, of the norms ft t in ZP. Here I should maybe, I just realized that there is a bit difference here when I talk about the LP norm. I should maybe define it maybe LQ norm, because at the moment we are using P as the number of elements in the group. So just to be like, because you can see that there's the P in the summation here, so you could actually define this LQ. It's a bit more consistent with the definition. And then here this would be LQ norm. Okay, so these are the kind of basic norm identities that we will encounter, and it's quite important that we make some kind of like use of this at one point. So as I said, like at one point when we talk about the random walks, we start to estimate this total variation distance, and the first thing we use is the L1 identity to get it into this L1 norm. But then after that, it turns out that it's useful to go to higher order LP norms. So like, for example, the L2 norm is important because it allows you to basically then transfer the analysis into this notion of Fourier transform later on. So that's why we will talk about later on, not in this lecture, but in the next one, we'll talk about, for example, the Cauchy-Schwarz inequality, and also like something called the Hölder inequality, which is basically a way to transfer from information, let's say from the L1 norm into LP norms or LQ norms of this type, or L2 norms. And maybe I can give you a couple of like properties that maybe I should mention over here. So I think I had this kind of basic thing. So the reason, I think the main like property why we are calling these as norms comes from the fact that so these satisfy the axioms of a norm. So that's the kind of basic thing that it's like the property. So there's like an axiomatic properties that we have for the thing. So which can be useful in some of the analysis that we are doing. But basically is that first of all, if you take the so let's here actually be the 1q. It includes the infinity actually, we can assume. Then we have the following property 1, which is saying that you have this kind of subadditivity or triangular inequality. So then f plus g at the point q is always at most fq plus gq. So that's always true. So this is true for any f and g zp to c. We have the following properties holding. So this is, I think this is some kind of triangle inequality or subadditivity. And the second property is this kind of homogeneity or scalability of the norm. So what you have here is that if you take, let's say a scalar, let alpha, I don't know, in our case we could like have it actually to be, let's say, a complex number. Then we have that alpha times f. If you take the q norm of this, then of course by the we could like verify this from the definition, but you get that this is the same as the modulus of alpha times the fq norm. So this you can take the constant out, and then the third thing is the kind of vain thing that is that this f q is 0 if and only if actually in our case we can actually get that this is well, we could put this that this is like, this implies that then the ff let's put it there, f is equal to 0. So it's just a 0 at those points, because it's a non-negative numbers you're summing. So of course when negative sum is 0, it's a finite sum, so it's equal to 0. And in literature you can then say that this is a norm space. So thus this the space of functions f from zp to c with norm, let's say this fq becomes a norm. So you can apply this kind of basic, let's say, for example, vector space analysis or norm space analysis for these functions to be able to get like basic properties of these things. That's kind of the main things that we actually need from the LP and LQ norms in this way. And the next time I'll talk about the kind of basic inequality that connecting, let's say, from P to Q or something like this. How do you do this kind of connection, which is important then to transferring, let's say, from the total variation distance, which we want to estimate ultimately in this course, to an estimate that involves, let's say, the L2 norm or LQ norm that is maybe easier to analyze in the context of Fourier analysis. So that's kind of the next goal that we want to talk about for these LQ norms. So that's all. Thanks.